Okay. First of all, thank you for the ICGES for allowing me to speak on a subject that I have talked about in conferences around the world to a number of different audiences. The subject is climate change and the energy transition 2021 to 2030, a reality check. And the presentation really has three different parts to it. First part is a summary of where we are with regard to climate change. The second part is talking about the situation with regard to the IEA net zero plan. And the third part is, given that the two pieces seem to be incompatible, what do I think really will happen during the next decade? So to start out, 2020, and I see you move to the next slide now, was an important and instructive year in addressing climate change, because despite the reduction in greenhouse emissions, a solar minimum, which was a lower level of solar energy, and a La Nina ocean current, which is often connected to lower temperatures, 2020 actually tied 2016 as the warmest year in recorded history, although some areas were much warmer than others, Northern Asia being particularly warm. And increased temperatures resulted in more intense storms, heat waves, wildfires, droughts, and floods. And as you can see on the chart on the right, the number of weather-related disasters have increased by fourfold in about 40 years. And 2020, actually, it's not on the slide here, but 2020 was the worst yet. And the other interesting factor is, despite a 4.3% reduction in world energy use, renewable power actually increased during 2020 by 5%. Which indicated its cost competitiveness, advances in technology, and potential for future growth. And oil as a transportation fuel suffered the greatest loss due to the lockdowns, almost 10%. So if we can move to the next slide. So with the need for urgent action to address climate change to try to limit the 1.5 degree temperature rise, the International Energy Agency issued a report on a path to net zero by 2050, and many nations made expanded pledges to reduce the greenhouse gas emissions in the coming decade. And if you take a look at the graph, it shows that most of the emissions actually are coming from the emerging market and developing countries. But then when you take a look right below at the pledges to cut emissions, you notice that all those pledges are coming from the advanced economies. The US and the EU, for example, a 50% reduction versus 2025, and Canada and Japan at 45%. And despite the good intentions, the EIA roadmap has no realistic possibility of being accomplished. Now, there are many reasons for that, but as we go later into the presentation, I'll point to the three most prominent ones. One is that 70% of the world's greenhouse gas emissions are outside the OECD countries, and these countries have no plans to cut emissions in the coming decade and are dependent on economic growth to raise living standards. The second problem is the plan depends heavily on continuing exponential growth in renewables, but these renewables require quantities of certain minerals that far exceed the current supply, and the investment to increase the supply has not been made. And the third problem is the actual share of renewables in the past decade has not increased, and as the share of the energy grid increases in specific markets, the lower level of reliability becomes apparent. And also the effects of climate change on renewable energy needs to be addressed. However, there is a recognition of a climate emergency. So what is likely to take place? So let's go to the first part in terms of what is the actual status of climate change. Now, next slide, please. The climate change is an accelerating process. Interestingly, The temperature rise during the first half of the 20th century was due to increased solar activity. And the solar activity then began to decline again from about 1950 to 1975, which masked the effect of the rising greenhouse gas emissions. And then since 1980 is really when the temperature has started to rise. And in the past 40 years, it's risen by about 1 degree centigrade, or about 1/4 degree per decade. Now, if you look at the maps, you can see that rise has not been uniform. Land has risen, the temperatures over land have risen faster than the ocean, and the Arctic has warmed fastest of all, or about 3 times the global average. And if you notice, there are some anomalies there. For example, the area south of Greenland, due to the melting cold water from the glaciers, has actually cooled during this coming year. And in the Antarctic current in the South Atlantic, the temperatures have actually warmed over the ocean the fastest of all. And the implications of that will come out a little clearer later in the presentation. Next slide, please. Now, the increased temperatures were noticed since 1980, but since 2000, something else has happened. And the different aspects of the increased temperatures have started to coalesce, which has accelerated the process. And I'll just mention some of them. One is reduced snow cover. Obviously, as it warms in the Arctic, you have less and less snow cover during the spring and the summer. And snow reflects sunlight. With the warming temperatures, the amount of land covered by snow is reduced. And just by 2 million square kilometers in this century, in the past 20 years, with more heat absorbed and land temperatures. Another factor is melting permafrost. As the Arctic melts, methane, a more potent greenhouse gas than CO2, is released as the permafrost melts. Permafrost covers 20% of the world's land area. And since 2000, 15% of it is melted. And by 2030, it's going to reach 30%. Another factor, if you move the slide a little further, you can see the bottom of the slide, is the weakening of the jet stream. Now, the jet stream is a belt of air which sort of protects the temperate latitudes from the cooler air in the Arctic. And as the Arctic warms much more faster than the rest of the globe, the temperature differential is weaker, and so the jet stream wobbles. Now, it is always wobbled to some extent, but those wobbles are becoming more and more extreme. And just a few examples of that: in 2019, it wobbled to an extent that an air mass over the Sahara actually made it over Northwest Europe, raising temperatures to close to 40 degrees centigrade in Paris and London. And actually, it continued north over Greenland, raising temperatures more than 20 degrees over the Greenland ice glaciers, causing the greatest melt in recorded history. Another example that we've seen more recently, just last month, was a wobble and a heat dome over the Pacific Northwest of the US, which raised temperatures 45 degrees, almost 50 degrees over Seattle, Portland, and southern Canada. Now, the reverse happened in February in the US, in what was called a polar vortex, where Arctic temperatures made it all the way down to the state of Texas, where I actually personally saw that, where temperatures reached 0 degrees Fahrenheit. That's not 0 degrees centigrade, but 0 degrees Fahrenheit, causing a major power loss and disaster of loss of life and over $100 billion of economic loss. So these things, which were once in a decade or once in a lifetime, are now happening every year and will continue to happen every year. Next slide, please. So you can think of this climate change happening in 3 phases. Phase 1 was 1980 to 2000, where temperatures began to increase beyond the range established in historical times. Then 2000 to 2020, which was a cascading and compounding effect where the different aspects began to coalesce. And now we're entering the third stage, which is climatic tipping points, which if significant steps are not taken, these tipping points will they're not one-off events, they will basically change the climate of the planet. And just mentioning them, the Amazon rainforest, basically changing the climate there, taking away the major lungs of the planet. Arctic sea ice, the elimination of the summer Arctic ice pack, the Atlantic circulation, overturning of the Gulf Stream, the boreal forest, the massive fires and changing of the forests in Arctic forests in Canada and Siberia, dying of the coral reefs, melting of the Greenland ice sheets, thawing of the permafrost and the West Antarctic, breaking off of the West Antarctic ice sheet and at a later time, East Antarctic ice sheet. So all of these things are starting to happen. The question is whether they become irreversible. And on the next slide, I mean, we don't have time to go through all of them, but I'd just like to highlight 4 of them, which are probably the 4 that we're approaching the closest. One is an ice-free Arctic summer. Now, in just 25 years, from 1995 to 2020, the amount of ice cover in the Arctic has been cut in half, from 7 million to 3.5 million square kilometers. That's how fast it's come. And by the middle of this century, the Arctic will be ice-free in the late summer, except for just a skim of ice along the northern coast of Greenland and the Canadian islands. So, does that have any other effect other than just affecting the Arctic area? Well, it speeds the whole process. And there are a couple of reasons. One is that ice reflects heat. More than 90% of the heat is reflected back from sunlight, whereas the ocean absorbs about 90% of the heat. So this will, as it's covered by the ocean, it'll speed the process. Another factor is the currents in the Arctic. Right now, most of the ice that melts in the summer goes right up into evaporation. But as a larger portion melts, more of it is sent by currents down into the North Atlantic, which will speed another process. And a third factor is that areas, as the ice pack reduces, it doesn't reduce uniformly. It's basically reducing off the coast of Alaska and Siberia. And those areas are having more and more periods without ice next to them. And so those areas are warming much more faster than other areas. Climate change in the Amazon. Due to deforestation and global climate shift, Amazon climate is rapidly changing and losing moisture. You can see from the dark green there is basically the Amazon rainforest. And the colors, the yellow, orange, and red are the areas of deforestation. So about half of the Amazon now is undergoing rapid deforestation, and about 20% of the forest is gone. And the map on the right is from space, a measuring of the humidity or the water vapor. And what it shows is that the humidity in that area is rapidly decreasing. And so half of the Amazon is turning into a savanna, which has a major impact on the overall carbon cycle. A third problem is sea level rise. Sea level has been rising steadily in the last 20 years. It now averages about 4.5 millimeters per year. And if it continues rising and accelerating at the rate it is now, you're going to have up to 1 meter rise by the end of this century. But that's not the real danger. The real danger is that West Antarctica has been warming at 3 times the global rate. And because the South Antarctic current is warming much faster than the rest of the ocean, the West Antarctica is being undercut. Now, West Antarctica is basically all ice. None of the land is above sea level except for very small portions. So the West Antarctic glaciers are melting from above sea level and being undercut from below. And the possibility of large portions breaking off is becoming increasingly likely. And this actually happened about 13,800 years ago, in which large portions broke off during the end of the last ice age. And that's called Meltwater Pulse 1, in which over a 300-year period, sea level rose by an average of 40 millimeters per year, or 1 meter every 25 years. So that's very possible. The last piece I want to mention here is weakening of the Gulf Stream. Now, as more and more ice melts off Greenland, it causes a blockage of the Gulf Stream. And one of the aspects is that warm water has been building up off northeastern US, causing a higher temperature rise there than the rest of the states. But the Gulf Stream now has lost about 15% of its velocity and amount of water movement. And oceanologists expect that if it hits about 35%, it comes to a tipping point and it gets overturned. And from a modeling of what will happen there, basically the Gulf Stream is a heat transfer from the south to the north. And if that stops, the northern hemisphere will get a lot colder and the southern hemisphere will get a lot warmer. That's not rocket science. So this goes from something that was out of a Hollywood movie to something that very possibly could happen in the century. So when we talk about the biggest factor in climate change in the next slide, since 1980, it's obviously the composition of the atmosphere. And there are two main gases. CO2 represents 76% of the greenhouse gases, with 80% of the emissions due to the burning of fossil fuels. And as you can see from the slide there, that really has taken off since the end of the Second World War. Coal, oil, and gas. And if you'll notice, the coal amount increased by 40% just in one decade, from 2000 to 2010. The amount of CO2 increase per year has increased from about 0.8 to about 2.5 as more and more CO2 goes into the atmosphere. Methane represents 16% of the greenhouse gases, 60% from man-made processes, 40% from natural processes, and a third of the man-made processes come from fossil fuels. The other 2/3 come from agriculture. Methane is 80 times more potent greenhouse gas than CO2 per molecule in the long term, 25% in the short term. So you say, okay, well, that's good. But one of the problems there is if you take CH4 and break it down in the atmosphere, it turns into two things for the most part, H2O and CO2. So as methane breaks down, it puts more CO2 into the atmosphere. So that's kind of a mixed blessing. Since pre-industrial times, CO2 has increased by 150%. Methane, the level is 150% higher, methane 250%. So methane is increasing faster than CO2. It was 10% of the greenhouse gases in pre-industrial time, now it's 16%. And from the fossil and sedimentary record, we can establish what CO2 levels were in the geologic past. In the early part of the Cenozoic, it was about 800 parts per million. That was a time which the Earth was much warmer, much higher sea level. And then about 3 million in the Pliocene, it dropped below 400 parts per million. The Arctic ice cap formed. During the glacial and interglacial periods, it was ranging between 180 and 280. We're now at 420. And not surprisingly, the Arctic ice cap is gone. So that puts us in the historical record. We're basically back in the Pliocene, and if we keep going, we're going to go much further back in geologic history. So to sum it all up in the next slide, we can go to the next slide, please. The human influence on climate can be measured by radiative forcing, which is just a way of putting all these pieces into a clear pattern. And the two most significant factors, of course, are CO2 and methane. And interestingly, the two countervailing forces are aerosols and cloud adjustments from the pollution that we put into the air. So, one of the worrying factors and challenges we place is if we take away a lot of the coal burning and take away the pollution, we're actually letting more sunlight into the air and increasing the warming process. And an example of this is why was 2020 so warm? It was warm because of the lockdowns in the first half of the year and the reduction of pollution. So that's a challenge that we have to face. So when we put everything together, the radiant factor, or the RCF, is about 2.3 from pre-industrial times, and it's increasing at an amount of about 0.3 every decade. And so the earlier projections of can we limit this amount to 2.6 is we're just not going to be able to do it. We're going to be at that point by around 2030. Next slide. So with the obvious urgency of addressing climate change, why is it so difficult to find solutions? There are a number of different problems, and I'll just point out the big three. Problem number one is that 73% of our current emissions come from emerging and developing nations, and their prime concern is improving living standards of their populations. They account for the entire growth of greenhouse emissions in the past 50 years. If the developed nations honor their pledges for emissions by 2030, they're only going to be 16% or 1/6 of the emissions. If you can see from the slide, the peak of CO2 emissions from North America and Europe was actually reached 50 years ago. And in this in this century, they've actually dropped by about 20%. So that's not where the problem is right now. And putting it in another way, I think another clear way of looking at it, you've got two factors. You've got the GDP and the total energy supply. And then as countries advance, they start to become more energy efficient. And over the 21st century, the world in general has been increasing its energy efficiency by 2% per year. And it's been increasing its GDP by 3.5% per year. So it's been increasing its energy use by 1.5% every year. Now, Europe and North America have been increasing their efficiency by 2% and increasing their GDP by 2%. So their energy use has been flat. And as they've started to switch from coal to natural gas, their emissions have dropped. The difficulty is in Asia. And Central Asia and Southern Asia covers India, the subcontinent. Eastern Asia is China and Southeast Asia. And in those places, they've actually been even better in increasing their energy intensity. They've been getting better by 2.5% per year, but their GDP has been growing between 5 and 6% a year. So their energy growth has been between 2 and 3% a year. And unfortunately, they've been using coal to a large extent in that, so that their emissions have been growing up. Now, Africa and the Middle East have not been getting more efficient as much, only 1%, and they've only been growing about 4%. So their GDP has been going by 3%. Australia and New Zealand, Oceania, have been about like North America and Europe. So there's your problem. That the GDP is going faster than they're getting energy efficient. Next slide, please. So the problem here is Asian economies, and mostly China, are committed to coal. The slide on your upper left shows the number of new coal plants that have been opened, and you see in China, it's still dominantly coal. The rest of the world has been shifting. More coal-fired plants are being retired than are being built, although some still are being built. And if you look at the age of the coal-fired power plants in North America and Europe, most of your plants were built in the 1970s and the 1980s, and those are the ones that are being retired. Whereas the ones in Asia and predominantly China have been built after 2000, and these have a 40-year life. So they're going to be around for a while. The pledge for China is to reach peak emissions in 2025 and reduce after 2030. And India is to a much lesser extent than China, but it will pass the US in this decade to be the #2 emitter in the world. So let's actually put some numbers to this. Let's assume that the US, Canada, and the EU fulfill their emission pledges. They're very ambitious. They may not make it, but let's assume they do. And then let's take the rest of the world at what their commitments are right now. Asia Pacific and the rest of the world will average 2% increase through 2025 and then gradually bring it down to zero by the end of the decade. So North America and Europe's share of emissions dropped from 36% in 2010 to 27% where they are now to 16% in 2030. And you put that all together, and what it means is the good thing is CO2 emissions will stop rising. But the bad thing is that they'll flatten out. They really won't drop in the coming decade. We'll go from rising CO2 emissions to CO2 emissions basically being flat. And we'll talk later about what that means for climate change. So let's go on to the second problem. The second problem is the supply of minerals needed for renewables and batteries is far short of what is needed. And the investment to close that gap is not immediately forthcoming. The chart on the right shows the amount of minerals needed to reach the IEA Sustainable Development Scenario. Now, the Sustainable Development Scenario is a CO2 reduction of 100% by 2070. So this is not as drastic as the net zero by 2050. But what this shows is the amount of these minerals that are needed by 2040 in order to follow that path. And it shows that lithium needs 42 times the amount that we're producing today, 25 times graphite, 21 times cobalt, 19 times nickel, and 7 times rare earth. So this is not 420% of the lithium we're producing today. This is 4,200%. So looking at just in the next decade, for copper, for example, you're going to be about 33% short by 2030. Lithium, you're going to be 300% short, and cobalt, you're going to be about 70% short. So, your problem is that for major mineral projects, it takes 10 to 15 years from the time that you make the investment decision to when you actually start producing. Now, 10 years in areas that have good infrastructure, and 15 years in sort of greenfield areas. And so as you can see, the amount of investment from 2016 to 2020 did not increase. And to get those production levels, that number needed to be skyrocketing now. And it's not increasing. And so you've got a basic disconnect. And the next slide, I think, demonstrates exactly why you need those increased amounts of minerals. If you can move to the next slide, please. So one of the major factors that we're looking for is switching to electric vehicles. And in order to fit the sustainable development scenario, which remember is not a net zero, but it's an aggressive scenario, you've got to go from 2 million to 72 million electric vehicles during that time. Now, the amount of the minerals that are shown on the right that are needed for an internal combustion engine and car, the glider indicates the body of the car, is about 35 kilograms. For an electric vehicle, most of the minerals are needed for the battery, and they average about 200 kilograms. So an electric vehicle needs 6 times more minerals than a conventional vehicle. And so that's where your problem of going from 2 to 72 million sold per year comes. And if you move to power generation, for natural gas and coal, you need anywhere from about 1,500 to 2,500 kilograms per megawatt power production. For nuclear, it's about 5,000. For solar panels, it's about 7,000. For onshore wind, it's about 10,000. And for offshore wind, it's about 15,000. So you're not looking at well, you are looking at close to 6 times the amount for offshore wind, about 4 times the amount for solar. So again, you need much more of these crucial minerals for renewables, and you're just not putting the investment in, and it takes too long to get it. So you've got a basic disconnect there. So let's move to the third problem, and the growth of renewable power is far below what is needed. And the reliability is suspect. Now, to get to your net zero level, you're going to need an order of magnitude more wind and solar power by 2050. You're going to need double the hydropower. You're going to need double the nuclear power. Now, the driving of the increase in renewable power in the past 10 years has been the reduction of costs. And if you take a look at the solar cost and the wind cost, the solar went from about $250 per megawatt hour to about 40. The wind from 124 to about 40 again. Gas has dropped significantly, which is why it's still competitive. And coal and nuclear are far more expensive, which is why they've been falling by the wayside. But you'll notice that the increases or the decreases have been flattening. And you'll also notice that the amount of annual solar and wind that have been increasing has started to flatten out. As the cost has flattened out, the amount that's increased has begun to flatten out, unfortunately. And the only way we're going to make that kind of curve that you see on the left is if you continually increase it. And that's been the problem, is that the increase is, while impressive, has reached a kind of a plateau. And if you put it all together, the amount of renewables in the overall energy mix during the past 30 years has stayed constant at about 17%. Now, as what we call modern renewable, the solar and the wind has increased, to a large extent, it has been replacing the traditional biomass in a lot of the developing world. And what we need to do is we need to get that green curve up above 17%. We need to start reducing the fossil fuel use. So we really have not made inroads where we need to make it. The second piece that we need to look at with regard to renewables is their reliability, which is shown on the next slide. And this is just an inherent problem in the renewables, which it is what it is. The EU has gone further than any other area of the world in putting the renewables into its power grid. And the slide on your left just shows the variation in the amount of power. And the advantage here is we're looking, there are two advantages really. One is you're putting wind and solar together. So the variability in each of them separately is a little bit compensated for. And the other point is you're looking at continent-wide, so that there are some areas of the continent that have sun and some don't, some have wind and some don't. But even with all those different factors, the amount of power produced by solar and wind varies from 30% to 10% of the grid, depending on the day, the time of day, and the actual day. So the variability is still a problem. And to dive down a little deeper into it, this is just the amount of solar radiation at a major solar plant in Spain, and the difference from a sunny day to a rainy day in the spring is 85%. And it is what it is. That's just an inherent problem. Looking at it from a seasonal standpoint, this just shows the amount of solar radiation received in Cincinnati, the United States, which is a moderate latitude place. And during the summer, you get 8 kilowatts per day, and during the winter you get 3 kilowatts per day. So it's a 3-to-1 almost difference between the summer and the winter. An example of when you have too much dependency on wind was an unfortunate and tragic example in Texas in February. You saw earlier about the polar vortex, where temperatures reached a level that had not been seen in 30 years, and the extent of it had not been seen in 100 years in Texas, where the temperatures dropped to 0 degrees Fahrenheit over much of the state for a period of several days. Now in Texas, they deregulated their energy grid in 2000. And over time, because it was the cheapest sort of source of power, the amount of wind power, the share, increased from 8% to 25%. And actually, during the winter, it rose up to over 30%. And about a week before the polar vortex, the wind just stopped blowing. Nothing nefarious about it. It just stopped blowing. And so the amount of power created by the wind turbines dropped from February 7th to February 9th from 25 gigawatts to 1 gigawatt. And so when the polar vortex hit about a week later, the excess capacity from the gas-powered turbines, for the most part, was used up, making, taking account of the lack of wind power. And so that was one of the major causes of the power disaster. So your problem is, once you start getting to a significant number for renewables, you're making yourself vulnerable. You need to have a large, consistent source of backup power somewhere. Next slide, please. Now, the one consistent source in many places is hydropower. And you need and for hydropower, you need water. And unfortunately, climate change is changing the climate and changing the availability of water in a number of crucial areas. One is in Southern Africa. The unprecedented drought, and the IEA puts Southern Africa as the #1 place in the world as risk for drought. And some of you may have been to Victoria Falls, very, very impressive. Well, in most of recent years, it's no longer Victoria Falls, it's Victoria Trickle. In 3 of the last 4 years, there's been almost no water there. And so as a result, the world's largest, Africa's largest hydroelectric plant, the Cahora Bassa, has had to significantly reduce output. Closer to home for us, there's been an historic drought in the southwestern US, and the Hoover Dam, which is the largest US hydroelectric plant, has reached Lake Mead, which sources it its lowest level in history, putting its viability in question. California, during the springtime, depends on hydroelectricity for 20% of its power. Well, during this drought in these 2 periods, that's been cut in half. So hydroelectric power, which right now is half of renewable energy around the world, is in question. And there's a bigger worry, and that is, if you take a look at a map, the Himalaya Hindu Kush contains the largest concentration of ice except the poles. It's often called the 3rd pole. The temperature at high latitudes is rising at rates similar to the polar regions, and by 2050, significant portions of these glaciers will have melted. And 38% of the world's hydroelectric power comes from the meltwater of those glaciers. So this is something that in the second half of the century, if things aren't turned around, will put hydropower at a significant risk. So there are other problems with the net zero plans, but these are the 3 significant risks, and they are significant. So let's go on to, given what's happening with climate change and what are the risks, what is likely to happen? So let's start with the immediate future. What is the world's response after 2020 regarding greenhouse emissions? And 2020 was a pretty significant year. Energy consumption dropped, CO2 emissions dropped, the largest amounts since the Second World War. In the US, fossil fuels will largely recover from 2020 due to the economic recovery. And because so many of the US power plants can switch from gas to coal, because natural gas prices are high, people are going to, those plants are going to switch back to coal. So the US, to a large extent, is going to come all the way back in its greenhouse gas emissions. By December 2020, world greenhouse gas emissions were higher than the 2019 level. And the estimation is that most of the drop of 2020 will be recovered by 2021. Coal demand is coming back very strongly from the drop in 2020. China, the producer and consumer of more than 50% of the world's coal, is planning to increase production and consumption through 2025. They approved about 2/3 of the world's new coal power plants in 2019 and 3/4 in 2020. The EU and the US will continue shifting away from coal after 2022, and the rest of the world coal use will probably start to drop after 2023. The coal markets, if you move the slide down just a little further, the coal markets at least will stay strong through 2023. However, and if we go to the next slide, what I believe will happen is the coming decade will finally see the beginning of a shift away from fossil fuels. The amount of electric vehicles will begin to make an impact, although probably not as fast as they think. The world energy use growth will continue to go at 1.5% per year. I just don't think there's any way around this, because the developing world is going to continue to work to improve the economic prospects for its citizens. Hydro growth is going to be steady the way it's been before. The nuclear power growth, unfortunately, it's not going to happen, because the plant retirements in the US and EU are going to be balanced by new plants in Asia. The renewable growth will continue at the rate that it's been going. However, there is going to be a spurt of additional growth in offshore wind. Oil demand will plateau and begin to decline by the end of the decade. Natural gas will take up the gap with continued strong growth, particularly in LNG. And coal will begin to significantly decline with shift to gas. So what will this mean? Fossil fuel has been consistently at about 85 to 87% of fossil fuel energy. By the end of the decade, it will finally start to drop. Oil has been the transportation fuel. 60% of oil use is transportation fuel. Now, interestingly, in 2020, global car sales decreased by 15%, but electric car sales increased by 40%. If electric car sales continue to increase by 40% per year, by the end of the decade, it will have a material effect on oil use. Another interesting factor, after the pandemic, 30% of white-collar work is likely to continue from home compared to 10% before, and that will also reduce the amount of transportation. And the global number of operating coal plants actually began to decline starting in 2018, leaving China really as the only area that is still increasing its coal use, and that will finally start to switch by the middle of the decade, and so coal use will finally start to drop. Next slide. So, what needs to happen to actually start to begin reducing greenhouse gas reduction this decade? What are steps that we can actually start to take? The number one step is carbon pricing, a market-driven solution to shift to a lower carbon economy. Now, this is happening in fits and starts all over the world in different ways, but this absolutely has to happen to make everything move in the right direction. The EU is is at the forefront of this, and you're going to really need a price that is somewhere in the order of $40, $50 a ton to make a significant difference. Carbon capture, use, and sequestration, we know how to do this, and it could be implicated on a major scale quickly. And the interesting thing there is, once you have carbon pricing, this will become economic, and this will take off in a big